today's class, as I said, we'll solve few more problems based on angular momentum conservation. And if time permits, we will discuss the third kind of motion of a rigid body, which is combined translation and rotation. Okay. Look at this situation, all of you. Suppose there is a smooth horizontal table. Okay. What you're seeing here is the top view of the system. A rod is pivoted on the table at a particular point. The rod's mass is m, its length is L, and there's a particle moving towards the rod. Particle's mass is m. It's moving with a speed u, as you can see. Okay. Initially, the rod is at rest. Yusuf, can you describe what will happen as time passes? No response. Maybe he will type in chat. Rishi, tell me what happens to this system.
There is the ball will roll and at the speed u, and then it will disturb the rod. It'll move towards
Okay.
the rod
Think
will
of it as
move.
a small particle only, or something like a carom coin. Don't think of it as a ball. Okay. Carom coin or a very small coin. You think of it that way. Yeah, it will continue moving with the speed u. It hits the rod and then
And then it'll hit the end of the rod and it'll go upwards. Like the rod will go upwards.
see, this is not up and down. Okay. On screen, it looks like it goes up. Everything is happening on a table. Okay. So you are saying the rod will start rotating.
Yeah, yes, sir. Left side will go rotate.
You should say anti-clockwise. Okay.
Oh, okay.
What about the particle? What could happen to it?
Depending on the force, sometimes it might hit the edge of the table, and then
No, no. Just after hitting the rod, what could happen to it?
its path will change.
Possibly. Okay. Its path could change. Okay. It could come to rest also. Or if it is a sticky particle, it can stick to the rod. Okay. Many possibilities are there. Okay, fine. So suppose you are told that the particle comes to rest after striking the rod. Particle strikes the rod and comes to rest. You know the rod will start rotating after this collision. Calculate the angular velocity with which the rod begins to rotate. That is the question. Derive angular velocity of the rod just after collision. Okay. Let us discuss a little bit. There is a collision happening here. Okay. But what you are asked to find out is angular velocity of the rod just after collision. Usually in collisions, what concepts do we apply? Vanilla.
The conservation of linear momentum.
The collisions that we had discussed before in work energy power, they were all uh, like none of them involved rotation. We never considered rotation. So there we used to apply conservation of linear momentum. What other ideas do we use in collisions usually? We used to use something called coefficient of restitution. Okay. Based on coefficient of restitution, you tell the nature of collision. Okay. And there were some special cases also. A very small particle collides with a very large object, then large object's momentum will not be disturbed, or large objects motion will not be disturbed. We used to consider cases like that. Fine. Here, when the particle goes and collides with the rod starts rotating. The rotational state is getting disturbed. Okay. So like you have to visualize. I'll give you some time. You have to visualize the forces acting during the collision. Okay. And think of what all concepts are applicable. And now you have some extra knowledge also. No, you know angular momentum conservation. You may try to do that because angular momentum equations will involve omega. Linear momentum equations won't involve omega. So linear momentum may not be helpful. Angular momentum may help. Okay. Energy wise, we can't say anything, okay, because we won't be able to use energy conservation, because in collisions, except in elastic collisions, partially inelastic and perfectly inelastic, some energy loss will happen, mechanical energy loss will happen. So we won't be able to write equations based on energy. We don't know how much energy is being lost. But one thing you are told is that particle strikes the rod and comes to rest. So you know what happens to one part of the system. You should find out what happens to the other part of the system. Whenever such questions are asked, usually it is momentum conservation that helps. You think whether linear momentum conservation should be applied or angular momentum conservation should be applied in this situation, and try to proceed. Try this, all of you. I'll give you all 3 minutes. Okay, I should mention how the particle is striking the rod. The particle strikes the rod at the end of the rod, and it strikes the rod in a direction perpendicular to it. That is how it was moving initially. Okay, particle strikes the rod at the end. Based on that, you solve. Let's see. Vanilla, how are you trying to solve this? Just tell me some ideas that you used.
Sir, I applied conservation of angular momentum.
Okay. Did you get any answer?
Sir, I got omega equal to U by L.
U by L. We'll see. We'll see. Rishi, how did you try to solve this?
Sir, I'm not sure.
Okay. Yusuf, if you can unmute.
I'm not sure, sir.
Okay. So there's a collision happening. So some kind of momentum should be involved here. Otherwise, we'll not be able to solve. Let's see. Particle goes and strikes the rod. We are looking to find omega of the rod after collision. Linear momentum equation will not involve omega at all. I mean, there is a way it could involve omega. Linear momentum of a system is mass multiplied with velocity of center of mass. In a rotating system, velocity of center of mass can be written in terms of omega. Okay, because every point of the system will be executing circular motion. VCM can be written in terms of omega. So maybe that way we can get omega by writing linear momentum equation also. But let us check. Can one of you tell me what is the condition under which linear momentum is conserved? When is linear momentum of a system conserved?
Sir, F net equal to 0.
When the net force on the system is 0, correct. Now imagine this particle going and striking the rod. Will the particle's velocity change before it strikes the rod? Will the
No, sir.
particle's velocity change before it strikes the rod? It will not. There's no reason. There's no friction on the table. It's a smooth horizontal table as given here. So particle's velocity won't change. So it will strike the rod with a speed u. When the particle just strikes the rod, imagine the forces they exert on each other. The rod will exert a normal force on the particle this way. Okay, this will be an impulsive normal force. Okay, it causes a sudden change in the motion of the particle, and it also causes a sudden change in the motion of the rod as well. This is an impulsive force. Okay, so one normal force acts on the particle, another acts on the rod. It is told to you that the particle comes to rest. So particle's momentum may go to the rod, but that will happen if net force is 0. Let's see. Obviously, this normal force is an external force on the particle. So net force on the particle is non-zero, its momentum gets disturbed. And that's clear. Particle strikes the rod and stops, no? So its momentum is definitely getting disturbed. Rod was initially at rest, starts moving. Its momentum is also getting disturbed. It's the system's momentum that we want to see if it is conserved or not. Okay. Now these two normal forces, they become an internal force to this system. Then can we say that the net force is 0, therefore linear momentum is conserved? Or are there any other forces acting on this rod when the particle collides with it? Just tell me what you think. Okay, take a minute, think carefully. My question is, are these two normal forces the only forces acting while they are colliding?
Sir, mass of the rod also.
Weight of the rod. Okay. See, particle will have weight, rod will also have weight. In which direction do weights act?
Downwards.
Downward means in like as seen by you, you tell. On the screen, how do you describe?
Into the screen.
Into the screen. Will they have any component in the plane of the screen, or will they have any component in the horizontal direction? They won't. Okay.
No.
Rod's weight and the particle's weight will both be acting perpendicular to the table. They won't have any component on the table. Even if they do, okay. See, weight of an object is a constant force, right? Weight is a constant force. Now, collision happens in a very small duration. Listen to this, all of you. We never talked about this before. Weight is a constant force. Collisions happen in a very short duration of time, dt. Then impulse means change in momentum. Okay. Impulse due to gravity, okay, due to weight of a system will be impulse. How do you calculate? Force multiplied with the duration for which the force acts. The force is mg, which is a finite value, small finite value, multiplied with the time in which a collision takes place is dt only. Okay. Now dt is something which tends to 0. dt tends to 0. mg cannot tend to infinity. Mg is not an impulsive force. It cannot increase its magnitude suddenly. It's a fixed amount of force. Okay. So this is a finite amount of force, finite and fixed amount of force. If you multiply such finite and fixed terms with something which tends to 0, the whole thing will tend to 0. Okay. Therefore, gravity is not an impulsive force. Gravity cannot cause sudden changes in momentum or motion of a system in a short interval of time. Gradually it can, but suddenly it cannot. We experience this in daily life also, no? Due to weight, nothing happens suddenly. Okay. Gradually, yes. Do you all understand this point or not? Any doubt in this? Okay. In this problem, gravity does not play a role at all because gravity has no component in the plane of the table. But even if gravity has a component, what I'm saying is during or in the short duration in which a collision takes place, gravity won't show significant effect on the system. You can ignore. Okay. Now see, I told you this one. We are discussing all the concepts in detail. We know that this normal force causes an abrupt change in the motion of the particle. It suddenly disturbs the state of motion of the particle. Such forces which cause sudden disturbances in the state of motion are called impulsive forces. Now you may say, sir, normal force also acts during collision only, no? And collision takes place in a short time only, no? How is normal force becoming impulsive? Impulse due to normal force is normal force multiplied with dt. dt still tends to 0. But what happens is normal force is a very large value there. It's a large force acting for a very short interval of time. Then the product, a very large number multiplied with a very small number, will be a finite number. That is what impulsive forces do. Okay, they are large magnitude forces which act for a very short duration, but still the magnitude of force, which is very large, multiplied with the duration, which is very small, will be a finite change in the momentum of the system. Okay, they will produce a finite impulse. That's the difference between impulsive forces and non-impulsive forces. Anyway, so normal force here is an impulsive force. Let it be. But the net normal force on the system is 0, rod plus particle. Now, when I asked you what additional forces act on the system, one of you said weight of the rod, weight of the particle. Now, we have eliminated the possibility of weight disturbing the system. Are there any other forces which act on the rod plus particle system as they collide? Okay. Have you all ever played pen fight? Yes or
Yes,
no?
sir. Yes, sir.
Use of vanilla pen fight.
Yes, sir. Yes, sir.
No, sir.
You should play. It involves a lot of physics concepts. In fact, you'll understand something called center of gravity very well if you play pen fight. You'll understand the role of friction. You'll understand rotational mechanics if you play pen fight. A lot of physics is involved in there. Okay. So in pen fight, basically what happens, there are two pens, one belonging to one person, another belonging to another person. They have to knock the other pen out, okay, by striking with the pen. So the ones who played pen fight, you may have observed, suppose this pen is there, you hit it like this, okay, with your fingertip. You strike it like this, like you strike a carom striker. Then what happens? Rishi, you tell me, you have played pen fight. So if you strike it at one end, close to one end like this, how does the pen move?
Sir, it starts like rotating in this. It goes in a anti-clockwise manner, and then
It
whenever it hit the pen, it is
no, no. You just tell how it moves. After it hits another
anti-clockwise.
pen, a lot of possibilities are there. Sometimes it won't hit another pen. Your pen itself will fall off from the desk. Many possibilities are there. You are saying it spins anti-clockwise. What else? Will it stay there itself and spin always?
No, sir.
It moves forward also, no?
Yes, sir.
So what you see happening is something like this. It rotates as well as translates. It's a case of combined translation and rotation actually. If it is a free pen, okay, of course table will offer some friction. All that will be there. That's why I said you'll understand a lot of physics if you play pen fight. Like you'll understand where to hit to produce how much. Sometimes you won't want the pen to rotate. You will want it to only translate. Then your mind will automatically make you hit it at the center of gravity. If you apply force through center of gravity, no rotation won't be produced. The pen will move without rotating. And sometimes you will want more spin. Then you will hit it at the end, okay, as far away from the center of gravity as possible. So unknowingly you'll be applying a lot of physics there. Anyway, when you strike the pen at one end, what happens is the pen has a tendency to rotate, and the other end of the pen also has a tendency to move away from its place. Okay, so this end tends to move. In most cases, it does. Of course, you can hit the pen without moving that end also. That possibility is also there. We'll discuss that. We'll apply actual equations and find out where the rod should be hit such that the other end will not have a tendency to move. In fact, I think today's lecture will all be about this problem only. We are going to deal with it in depth. So this left end has a tendency to move. You are hitting it at the right end, but the left end tends to move. Now you see what is happening with this rod. The particle is hitting the rod at one end. If the rod or had the rod been free, would the other end have a tendency to move or not? From your experience of pen fight, you tell.
So can you repeat your question?
The particle is hitting the rod at its right end. But due to that hit, will the left end of the rod have a tendency to move or not?
Yes, sir, it will.
Yes. Had it been a free rod, the left end would actually have moved also. But this rod is pivoted. The left end has a tendency to move, but what will the pivot do? It won't allow the left end to move. So the pivot will also be exerting a force here. And we don't know in which direction it exerts force. Let's consider a random direction like this. Okay. So due to the impulse given by the particle at one end, at the right end, the left end of the rod will also have a tendency to move, but the pivot does not allow that end to move. That means the pivot should be exerting some force as the collision is happening. Is this point clear to all three of you?
Yes, sir.
Okay. If you have any doubts, you can ask me at any point. Fine. That's all. We have considered all forces acting on this system. Their weights we did not indicate because weights have no role to play in the horizontal plane. In this horizontal plane, these are the forces acting on this system. Now you all tell me, okay, now Rishi, you tell me, is the net force on the rod plus particle system definitely zero? Is it zero?
No, sir.
It is definitely non-zero. Okay, because this normal will balance. But what about force exerted by the pivot? It's an unbalanced force. Therefore, the net force is non-zero. And Yusuf, you tell me, if net force is non-zero, which concept cannot be applied or which principle cannot be applied? If net force is non-zero, which principle of physics should not be applied? Vanilla?
Conservation of linear momentum.
Conservation of linear momentum. So for this collision, we cannot apply linear momentum conservation. Okay. The next option we are left with is angular momentum conservation. Energy conservation will anyway not apply because we don't know what kind of collision it is. Okay. So only option we are left with is angular momentum conservation. Fine. The condition for angular momentum conservation is that net torque should be zero about a given axis. Now the lines of action of force are visible to you. One of you identify an axis about which the net torque on this system is going to be zero. Definitely going to be zero. Identify an axis about which the net torque on this system is definitely zero.
Sir, an axis passing through the pivot.
Yes, the axis of rotation of the rod itself. Okay, if you take this as the axis, Rishi, tell me, why does force exerted by the pivot not produce a torque about this axis? Why does Fp not produce any torque about this axis? I mean, based on what logic can we say that?
Sir, it's not perpendicular or normal to the.
Okay, not a satisfactory response, but anyway, the line of action of the force passes through the axis. Therefore, it cannot produce any torque. Okay. Next, there are two normal forces acting. Their lines of action are not passing through the axis. So this normal force creates anti-clockwise torque, but at the same time, this normal force creates a clockwise torque on this system as a whole. Okay. Therefore, the net torque due to normal forces also becomes zero. So about this axis, the one that I have marked in green, none of these forces can produce a torque. And if there is no torque producing force, you can conserve angular momentum about that axis. Okay, so net torque is zero about this axis and we are going to make use of that. And how do you apply angular momentum conservation? Initial angular momentum about that axis itself is equal to final angular momentum. Vanilla, is this what you did?
Yes, sir.
Okay, let's see. Yusuf, tell me, before collision, which part of the system was moving? Which part of the system was moving?
The right
before
end.
Which part of the system, which object of this system was moving is my question.
So the free end.
The rod was at rest before collision. What was moving before collision?
So the ball or the finger or whatever.
The particle. Okay. The particle was moving before collision. After collision, particle comes to rest. It's given to you in the problem that particle strikes the rod and comes to rest. So after collision, it's only the rod that moves. Okay. We have identified the axis about which angular momentum can be conserved or is conserved. So initial angular momentum is only that of the particle. Initially, rod was not moving. Should be equal to final angular momentum, which is only that of the rod, because finally particle is not moving. Okay. Rishi, tell me the formula for angular momentum of a particle. Particle's mass is given as m. Okay. Rod's mass is m. Then.
mv cross r.
Wrong. You write the formula 10 times, take photo and send me. It is mr cross v. Order should never be changed in a cross product unless you want negative answers. Okay. It is mr cross v. And how do we apply it in an easy manner? We find out the magnitude first. Magnitude of angular momentum of a particle is mv r perpendicular, or you can also use mrv perpendicular. This is only for magnitude. Direction you have to see and assign. Okay. The particle's mass is m. The speed with which it is moving is u. Can one of you quickly tell me from where to where should the distance r perpendicular be taken? In angular momentum formula, the distance r perpendicular is from where to where? Is my voice clear?
Yes, sir.
Okay. So from where to where is the distance r perpendicular?
From the point of application of force to the I don't know what you call it.
See, there's no force here. Okay, we are talking about angular momentum. You are thinking about torque. Okay, that's why I said solve some problems whenever we discuss anything in class. I'm telling this to all of you. Okay, r perpendicular is the distance from axis to the line of action of velocity. The line of action of velocity is evident here. You can clearly see. Then this becomes the perpendicular distance, which is nothing but the length of the rod. Okay, axis to the line of action of velocity of the particle. So initial angular momentum of this system, which is nothing but initial angular momentum of the particle, is mvl. Rod didn't have any angular momentum initially, so plus 0. Okay, and this mvl, what is its direction or the sense? If you want to find out the sense of angular momentum, you have to visualize the sense of rotation of the position vector. The particle's position vector about this axis initially is this. After some time, it will be like this. After some more time, it will be like this. It's an anti-clockwise sense. Anti-clockwise means out of the plane. So plus k cap you can take. Anyway, direction doesn't matter to answer this problem. But that is how you visualize the direction of angular momentum. Okay, the direction or the sense of rotation of position vector you will have to visualize. Okay, this should be equal to final angular momentum. Final angular momentum is the angular momentum after collision. And it is given to you in the problem that particle comes to rest after collision and the rod rotates. So let's assume the rod rotates with an angular velocity omega. After collision, its angular velocity is omega. Now particle comes to rest, so particle angular momentum is 0. Now we need to write an expression for rod's angular momentum. Rishi, tell me, what kind of motion does the rod execute after collision? Rotational motion. In pure rotation, what is the formula for angular momentum? Any one of you? What is the formula for angular momentum in pure rotation?
Sir, is it I omega?
Correct. I omega. About whichever axis the system is rotating, you have to take I about that axis and multiply with omega. Good. Now, one of you tell me, what is the formula for moment of inertia of a rod about that axis, passing through one end perpendicular to it? I hope you all are able to visualize the axis about which the rod rotates is perpendicular to your screen. Okay, it rotates around that line, which is perpendicular to your screen. What is the formula for moment of inertia of a rod about that axis?
ml square by 12.
No. రోజు అదే తప్పు
ML
ఫార్ములా
square
చెప్తావు 4 సార్లు రాయి. It is ml square by 3 multiplied with omega. That's all. Single equation gives us the answer. Okay. The m on the left hand side of the equation is the mass of the particle. The m on the right hand side is that of the rod. But in the question, it is given that they are equal. You can cancel them. So m and l get cancelled. You get omega as 3v by l or 3u by l, because u is the speed with which the particle was moving initially. Vanilla, if you applied this, how did you get the answer u by l? What mistake did you make?
సార్ అంటే రొటేటింగ్ ఆబ్జెక్ట్ యాంగులర్ మొమెంటం మర్చిపోయాను.
ఏం రాసినావు?
దానిగా నార్మల్ గా అప్లై చేసేసాను.
Okay, fine. So rod will be in pure rotation, and in pure rotation the formula for angular momentum is I omega. Apply that, you get the omega of the rod. Is this clear to all of you? Any doubts in this? Okay. Now let us just check. When we analyze the motion of this system, we found, or we considered the possibility that the pivot exerts a force on the rod. Okay, at one end of the rod it exerts a force. We considered that possibility. Let's find out the direction in which it exerts that force. We didn't know the direction. Okay, the direction in which the pivot exerts the force depends on the direction in which that end of the rod has a tendency to move. If that end has a tendency to move in the negative y direction, the pivot will exert force in the positive y direction to prevent it from moving. If that end has a tendency to move in positive y direction, pivot will exert a force in the negative y direction. But see, we are not in a position to actually find out which way that end tends to move. Okay, so based on that, we can't answer the direction of force exerted by the pivot. There's something else we can do. We can use physics. We can apply the basic idea of momentum or impulse, you can say. The rod plus particle system, if it loses any momentum, it has to be due to force exerted by the pivot. If it gains any momentum also, it has to be due to force exerted by the pivot only. So what we will do is, we will check what is the momentum of rod plus particle system before collision, after collision. Is there any change? If there is any change, that change must have happened due to force exerted by the pivot. So based on the change in total momentum of the system, you can tell what is the direction of force exerted by the pivot. Okay, we will do that. Now you know what happened here. Initially particle was moving, finally only rod is moving, and rod rotates anti-clockwise. Okay. One of you tell me, how much is the initial linear momentum of this system? Initial means before collision. Pawan, can you tell? I know you just joined, but I hope you understood the situation, what is happening here. Particle goes and strikes rod. What happens is what we are discussing. Okay, Vanilla, tell me, what is the initial momentum of this system before collision? System means rod plus particle.
M into U.
M into U. Direction?
M with J caps.
J cap, correct. Initially only particle was moving. So initial momentum will be particle's momentum, mass multiplied with velocity. It was moving in the positive y direction. So mu J cap is the initial momentum. Okay. Linear momentum, not angular momentum. Keep that point in mind. If we just say momentum, we refer to, it means we are referring to linear momentum. Next is final angular moment. Final linear momentum. Finally, what is moving? The rod is only moving, not particle. Rishi, you know that the rod is executing rotational motion, but what we want is linear momentum. How do you express linear momentum of a rotating system? Or what is the one single formula for linear momentum in any kind of motion? Okay, any of you, if you remember, you can tell. What is the formula for linear momentum of a system in any kind of motion?
So V equal to R omega.
V equal to R omega gives you speed or velocity. I'm asking linear momentum.
Velocity of center of mass.
That's all. You consider velocity of center of mass. Okay. See, in case you don't remember the formula, think from the basics. You need momentum of a system. System is a collection of particles. Then momentum of a system becomes collection of momenta of the particles. So m1 v1 plus m2 v2 so on up to mn vn. That m1 v1 m2 v2, that at least that should give you the idea that center of mass can be involved. m1 v1 plus m2 v2 so on up to mn vn is nothing but total mass of the system multiplied with velocity of its center of mass. Okay. Now what were we trying to do here? We were trying to find out in which direction the pivot exerts a force. And what is the idea we are using? We are seeing the total momentum of the system before collision and after collision. And if the total momentum has changed, it must have happened due to force exerted by the pivot. That is the idea we are using. Now, initial momentum is clear, mu j cap. Final momentum is mass of the rod multiplied with velocity of center of mass of the rod. Mass of the rod is m, that is given to you in the problem. Can any of you tell me how to find out velocity of center of the rod after collision? How to find out velocity of any particle in a rotating system?
So V equal to R.
V equal to R omega can be used. Okay. R is the radius of the circle in which that particular point rotates. Now we are interested in center of mass velocity. So visualize the center of the rod, C. Now just after collision, the rod rotates anticlockwise. So center of mass will have a tendency to follow this path. Means just after collision, center of the rod will be moving this way. So it's important to imagine all this. Okay. And make sure you are understanding everything. That's why I explain things slowly. The velocity of center of mass of the rod just after collision is this way. Okay. And it can be expressed as V is equal to R omega, where R is the radius in which that point rotates. The radius in which the center of mass rotates is L by 2 because the rod is hinged at one end. Therefore, this VCM becomes L by 2 into omega, and the direction you can assign is j cap. Okay. Therefore, the final momentum of this system is m L by 2 omega j cap. And omega is 3u by L, you can substitute that. Therefore, it becomes 3mu by 2 j cap. Interesting. Initial momentum before collision of the rod plus particle system was mu j cap. Final momentum, means momentum after collision, is 3mu by 2 j cap. Look at these values and Yusuf, tell me, has the momentum increased or decreased? Has the momentum increased or decreased? No response. Pawan, you tell me.
Increased.
Increased, obviously. From mu, it became 3 by 2 mu, means 1.5 times. From 1, it became 1.5. It has increased. That is what is interesting. We hit the rod in the y direction, and the support is also exerting a force. See, momentum has increased in the y direction. No? From mu j cap, it went up to 3 mu by 2 j cap. This is basically 1.5 mu. So from 1 mu, it became 1.5 mu, means the change in momentum, extra momentum that it got, is 0.5 mu in the j cap direction. Now, who would have given this momentum to the system? The net force acting on it. And the net force acting on it is the force exerted by the pivot, whose direction we did not know. Randomly, I drew the arrow this way, okay, for FP. But now we found that the change in momentum is in the y direction. That means force exerted by the pivot must have acted in the y direction. Okay, so the force exerted by the pivot during the collision must have acted this way. That is what is interesting. The force exerted by the pivot acted this way. What does that mean? It means that end of the rod had a tendency to go down, go in the negative y direction. Okay, so just after the hit, that end of the rod has a tendency to go in the negative y direction. That's why the pivot exerted force in the positive y direction. Obviously, what other explanation could be there? Okay, so let's go to that pen diagram again. When you hit the pen at one end, you know it rotates anti-clockwise and goes forward. Ultimately, the left end of the pen moves forward only. But what we are discussing in the problem is what happens just after the hit. Okay, so what happens just after the hit, had the pen been free, must have been something like this. Okay, it has a tendency to rotate and it has a tendency to translate also. Okay, it's a case of combined translation and rotation, which is the third type of motion. We'll discuss that after conservation of angular momentum. But due to spin being too high, the the left end of the pen would have actually had a tendency to go down like this. Okay, that is what should have happened. Okay, I'm not saying pen is identical to rod, but this possibility is there. Okay, so yeah, someone unmuted. Is there anything you want to ask?
Sir, I have a doubt. సార్ ఇప్పుడు ఆ పార్టికల్ వచ్చి ఆ రాడ్ ని కొట్టక ముందు గానీ ఆ ఫోర్స్ యాక్ట్ అవుతుంది కదా సార్?
You tell me, why is there any need for the pivot to exert force on rod before the particle strikes? What would have happened if the pivot was not there? Would the rod have gone anywhere?
No, sir.
Then pivot would not have exerted any force before the collision. అంతే కదా, ఎందుకు ఎగ్జర్ట్ చేస్తుంది ఫోర్స్? ఆ పాయింట్ మూవ్ అయ్యే టెండెన్సీ ఉంటే అప్పుడు దాన్ని ఆ ప్లేస్లో ఉంచడానికి ఫోర్స్ ఎగ్జర్ట్ చేయాలి. The rod did not have a tendency to move before collision. Then why should the pivot exert any force before collision? Clear?
Okay.
It is happening on a table, so don't consider the possibility of rod falling down and all. ఒక టేబుల్ సర్ఫేస్ మీద జరుగుతుంది ఇది. ఓకే, fine. So in the collision, we found out how much momentum change is happening. How did we find out? We first derived angular velocity of the rod using angular momentum conservation, and then with that omega value, we found out VCM of the rod. Then we found out final momentum of the system, initial momentum of the system, and we see that there is a change happening due to collision. And this change in momentum must have happened due to force exerted by the pivot. Okay. And this change in momentum is a positive change. It's happening in the forward direction, means pivot exerted force in the forward direction. Fine. Now try this problem, solve this problem, all of you. Okay, it goes on the same lines. I'm just changing the point where the rod strikes, particle strikes the rod, nothing else. Okay, I want you to find out the angular velocity and force exerted by the pivot. Let me erase all these, just a moment. You will have to visualize center of mass, all this anyway, line of action of velocity. Situation is okay, just slightly different. Imagine the particle hits the rod at its center. Okay, so it's moving straight towards the center of the rod. Again, particle mass is m itself. It's moving with a speed u. Perpendicular to the rod, and it goes and hits the rod exactly at the center. Okay, I want you to find out. Initially, rod is at rest. Okay, particle is moving. I want you to find out, first thing, omega of the rod after collision. That you'll do using angular momentum conservation. And then I want you to find out direction of force exerted by the pivot. Exact force we are not finding out anyway. Okay. It is again given to you that the particle comes to rest after collision. Okay. Under that condition, you solve. Solve this quickly, all of you. I'll give you 2 minutes. Okay, 3 minutes. Rishi, can you tell me how you applied angular momentum conservation?
So L initial is equal to L final. And
what is the expression for L initial? Which part of the system had angular momentum initially? Whichever part was moving, that will only have, no? Which part was moving?
so the small point.
Particle was moving. Okay. How much is its angular momentum initially? This is the axis about which you will conserve. Okay. Use of formula for angular momentum of a particle. Pawan, formula for angular momentum of a particle.
Sir, MVR.
MVR perpendicular. Okay. You either tell the proper formula MR cross V, or you tell the magnitude properly, MVR perpendicular. Okay. Can you tell how much is the initial angular momentum about that axis, Pawan? Initially only particle was moving. Yeah.
Sir, MU.
MU. How much is the perpendicular distance from the axis to the line of action of velocity?
Sir, L by 2.
L by 2. So R perpendicular is L by 2. Therefore, initial angular momentum is mu L by 2. This is that of the particle. Rod was not moving initially, so initial angular momentum of rod is 0. Finally, you are told that particle comes to rest. So particle angular momentum is 0. Rod angular momentum. Vanilla, tell me the expression for rod's angular momentum finally.
Sir, ml squared by 3 into
I omega, that is ml square by 3 into omega. That's all. Cancel ml, you get omega is equal to 3u by 2l this time. Simple. Rishi, why were you not able to solve this? Where were you stuck?
Sir, I got confused as to how to solve L initial.
Like we have been applying this in many problems. No? Okay, fine. Pawan, did you get this answer or where were you stuck?
Sir, answer వచ్చింది sir. కానీ doubt తో.
Sir, is this the same equation that you wrote?
Yes, sir.
Okay. Yusuf, what about you? Where were you stuck? I didn't hear anything from you. Okay, fine. Right, we got omega. The next thing you were asked to find out is the direction of force exerted by the pivot. Now, there are two ways to do this. The pivot, it holds one end of the rod. So if you know which way that end of the rod tends to move, based on that, you can tell direction of force exerted by the pivot. Another way is By looking at what happened to the system, momentum of the system, you can tell in which direction the force, the pivot must have exerted the force. Now we can do it both ways this time. In the previous problem, we used momentum and all to find out the direction of force exerted by the pivot. But in this problem, there are other ways you can use, other methods you can use. Visualize this. The rod is getting hit at the center. Okay, exactly at the center. Now, if you hit something at the center, will it have a tendency to rotate? From your everyday experience, you all tell me, if you hit something exactly at the center of mass, will it have a tendency to rotate?
No, sir.
It will not. So due to the hit given by the particle, this rod this time will only have a tendency to translate like this. Okay, it will only tend to move parallel to itself without rotating. Okay, just a moment, I'll have to adjust its length. Like this. Had it been a free rod, this is how it would have moved without rotating. So see what happens to the left end of the rod. It has a tendency to move like this. That is why, or that is how you can say that the pivot this time must have exerted a force in the negative y direction. Okay, just by imagining what is going to happen in the absence of the pivot, you can tell what the pivot would do. Okay, another way to do it is by finding out what happened to the total momentum of the system. Initially, only particle was moving. So initial linear momentum of the system is mu j cap again. Final linear momentum of the system. Finally, only rod is moving and rod is executing rotational motion with angular velocity 3u by 2l. Then the center of mass of the rod will have a tendency to move in a circle like this. And in that process, at this position, it will develop or it will gain a velocity in this direction, velocity of center of mass. If you use r omega, r is L by 2 for the center of mass and omega is 3u by 2l. Cancel this. So 3u by 4 is the speed of center of mass just after collision, and that's in the j cap direction. So final momentum is momentum of the rod, mass of the rod into velocity of the rod, 3u by 4 j cap. So 3 by 4 is 0.75 mu. Initial momentum of this system before collision was mu j cap. Just after collision, it is 0.75 mu j cap, means it has decreased by 0.25 mu. Okay, change in momentum is minus 0.25 mu j cap. Minus j cap means downwards. Change in momentum is downwards, means the net force is in the minus j cap direction. Whatever is the direction of net force, same is the direction of change in momentum. And what is the net force on this system? Pivot force. That way also mathematically you can tell which way the pivot would have exerted a force. Is this clear to all of you? Any doubt in this? Okay. Now observe what we found here. If you hit the rod at its extreme right, okay, the left end has a tendency to go down. Where are those pens? Yeah. If the pen is hit at the right, the left end tends to go down. Okay, I am considering pen identical to rod. But if you hit the pen exactly at the center, or if you hit the rod exactly at the center, the left end has a tendency to go up. Okay. So basically what it shows us is that if you hit the rod at this end, the left end tends to go down. But if you hit the rod exactly at the center, the left end tends to go up. Okay. And JEE people, okay, the ones who set JEE papers, they kind of like these situations very much. If a system behaves one way in one case and in another way in another case, then there must be one case where it doesn't do any of these. Okay, so there must be one point where you can hit the rod such that force exerted by the pivot is 0. It is not negative, it is not positive. Then there must be one case where it is 0 also. Okay, they'll ask you to find out this distance where you should hit the rod such that the pivot does not exert any force. Okay, let's try this. I'll copy the diagram, just a moment. The question now is to find out where the rod should be hit by the particle such that pivot does not exert any impulse at all. Like during collision, it does not exert any impulse. That is what we want. Okay. You all can start solving if you want. I'll have to make some changes in this diagram. Rod mass and length L, particle, we don't know where it is going to hit this time. That is what we have to find out. Okay. Let's say the particle is about to hit the rod. Just a sec. Is my screen visible to all of you?
Yes, sir.
Okay. So we have to find out where the particle should hit the rod such that force exerted by the pivot is 0 during the collision. Okay. So let's assume the particle hits the rod at a distance x from the pivot itself. Okay, instead of taking it from the other end, let's take it from this end. It will be easier for us to write equations. That's why I'm taking it like this. Same situation. I mean, same objects. Situation is different, of course. Same objects. Okay. Your aim is to find out the distance x such that force exerted by the pivot is 0. Can any of you tell me how to proceed? Okay, take 2 minutes, think about it. I'll ask you after that. I'll write the question here. Any idea, anyone? How shall we solve this problem?
The first we write angular momentum conservation and linear momentum conservation.
Good. That's all simple. Impulse from the pivot is 0. If the pivot is not exerting any impulse, then there is no impulse on the system at all. The last two problems, impulse exerted by the pivot was nothing but change in momentum of this system. Okay, because force exerted by the pivot is the only net force acting on it during collision. So whatever change in momentum happens due to force exerted by the pivot only. Now we don't want that to happen. Okay, there should be no impulse from the pivot. That means there should be no change in momentum of the system. That is the equation that you have to write. So you'll write two equations this time. Initial linear momentum. Okay, angular momentum is conserved anyway. Write that first. Initial angular momentum is equal to final angular momentum. And initial linear momentum is equal to final linear momentum this time. Because it is given to you in the question that the pivot should not exert any force. So see, understand what all you are expected to be able to do if you want to get into IIT. One thing is conceptual clarity should be there. But another very important thing and a very basic thing is that you should be able to convert statements into mathematical equations. See, impulse from the pivot is 0. Okay. You can write an equation based on that. That ability you should develop. Fine. So impulse from pivot is 0 means the linear momentum of the system does not change. So you can write an equation based on that. That is how you solve problems. Now, that is how you convert any normal situation into a mathematical form. Okay. Pawan, tell me, how much is the initial linear momentum of this system in terms of what you see on the screen? Initial angular momentum, sorry. How much is the initial angular momentum?
Sir, MUX.
Mu, perpendicular distance, is x, correct. Final. Particle comes to rest after collision, rod rotates. So how will you write final angular momentum? Rishi, final angular momentum?
Sir, 0 plus ml square by 3 omega.
Okay, particle's angular momentum becomes 0. Rod's angular momentum will be I omega. Its moment of inertia about that axis ml square by 3 into omega. Now here x is unknown, omega is also unknown. Okay, so you can't find out x from this single equation. We need one more equation. That's the linear momentum equation. Let's see. Vanilla, how much is the linear momentum before collision?
MU J cap.
Mu j cap. Yusuf, how much is linear momentum after collision? After collision, particle stops, rod rotates. So for a rotating system, how do you write linear momentum? Okay, you are saying it is 3 mu by 2. You don't know the angular velocity. You don't know how fast the rod is rotating. There's no way you can tell for sure how much its final momentum will be. Okay, anyway, final momentum is the momentum of the rod. Rod is a rotating object. For rotating objects, or generally for any system, linear momentum is mass multiplied with velocity of center of mass. Mass of the rod is m. What is the velocity of center of mass of the rod? You have to use v is equal to r omega. V is equal to r for the center of mass is L by 2. Omega is unknown. So L by 2 omega j cap. You can't say it is 3 mu by L, okay, or 3 mu by 2. That might have been the case in the last problem, not this time. Okay. Hope this is clear to all of you. We don't know the omega of the rod. So you can't tell the exact final momentum of the rod. You have to tell it in terms of omega. Okay, fine. Now what you will do, you will take omega from the second equation and put it in the first equation and get the distance x. Solve this quickly, all of you. Right. From the second equation, omega is 2u by L. Substitute it there. You get x as 2L by 3. Correct. Let's understand what this suggests. Okay. If you hit the rod, okay, uniformly distributed rod, if you hit it perpendicularly at a distance of 2/3 of the length from one end, okay, if you hit it like this, see, the rod doesn't simply translate. You are not hitting at the center. No, you are hitting it away from the center. So it definitely rotates. And you are hitting it on the right of the center. So it rotates anti-clockwise. And it translates also. You are giving it some momentum. So it moves forward. So a rod will move forward and also rotate in such a way that its left end doesn't have a tendency to move initially. So from that moment to the next moment, immediate next moment, if you visualize, this will be the situation. There is rotation. There is translation as well. The center has moved forward. Okay. The center has moved from here to here. And the rod has rotated. But the left end does not move. Okay. The translation and rotation will be balanced in such a way that the left end will not move. But that's only for one moment. The second instant onwards, that left hand also will have to move. It can't, I mean, the rod cannot rotate cannot always rotate about that end. Okay, that is impossible. If it's completely free, it can't rotate about that one end always. Okay, this is not possible. Just for one instant, it will behave like that. Okay, while the collision is happening, it will behave like that. That is what we have found. Okay, now that we talked about momentum, impulse and all, let's also introduce another term, angular impulse. Just the definition and basic calculation we'll discuss. Okay, one of you tell me, what is the definition of linear impulse, or the usual impulse that we talk about? What is the definition? Impulse J is equal to? Definition of impulse.
The force into delta T.
Force, that is a formula. What is the definition? What you said is correct only for the formula. Okay. Impulse is a sudden change in momentum. Okay, so basically it's a change in momentum which happens in a very short interval of time. And this can be calculated as force multiplied with the short interval of time. Okay. Then what will angular impulse mean? Linear impulse is change in linear momentum. Angular impulse will be change in angular momentum. That's all. So there's no particular symbol also for it. We just write delta L, which is change in angular momentum. If you want to calculate it, you can calculate it as final angular momentum minus initial angular momentum. You can also calculate it this way. Torque multiplied with the time for which the torque acts. Okay. Just like force multiplied with time for which it acts gives you change in linear momentum. Torque multiplied with time gives you change in angular momentum. Okay. It basically comes from this. Net torque is dl by dt. Therefore, dl, small change in angular momentum, is net torque into dt. Integrate that. You will get the total change in angular momentum, which is basically angular impulse, is integral net torque dt. If the torque is constant, you can write it this way. Same for linear impulse also. If the force is constant, it is f delta t. Otherwise, it is integral f dt. Area between force time graph. Okay. But see, there is another way also of looking at it. Net torque, or basically torque, is R cross F, right? So you can write change in angular momentum as net torque multiplied with time, R cross F multiplied with time, and force multiplied with time is change in linear momentum, that is linear impulse. Okay, there is, you can look at it this way also. Therefore, angular impulse is R cross linear impulse. You can calculate it this way also. Is this clear to all of you? And how do you calculate R cross linear impulse? If you only want the magnitude, it is R perpendicular multiplied with linear impulse. Or you can also do it this way, R multiplied with impulse in the direction perpendicular to R, if you only want magnitude. Is this clear to all of you? Simple, you can draw an analogy. Linear impulse is change in linear momentum, angular impulse is change in angular momentum. What changes angular momentum? Torque. So angular impulse should depend on torque. Delta L is equal to integral tau dt. Okay, if you take tau as R cross F, then you will see that delta L is equal to R cross J. angular impulse is r cross linear impulse. Again, as usual, r perpendicular here becomes the perpendicular distance from axis to line of action of linear impulse. If you want r cross v, then r perpendicular is from axis to line of action of velocity. If you want r cross f, r perpendicular is from axis to line of action of force. If you want r cross j, then r perpendicular is from axis to line of action of j. Linear impulse. Simple. Okay. So in questions like this, they can even ask you, what is the angular impulse given to the rod? And now you know what is angular impulse. Now final angular momentum minus initial. You can do that easily. Okay. Let's quickly go through what all we discussed today. So basically it was all about conservation of angular momentum and some additional things. Okay, how to find out the direction of force exerted by the pivot, how to make use of omega to get velocity of center of mass and momentum, linear momentum in such situations, all those things. Okay, and those of you who have never played pen fight, play. It will teach you a lot of physics about rotation and all. Okay, thank you all. I'll send you a worksheet tomorrow also. Solve it. It will be based on conservation of angular momentum in rotating systems. Next class, Wednesday, we will discuss the third kind of motion of a rigid body called combined translation and rotation.